Hello guys, welcome back to my channel, mathszoneafricanmotives, working on industrial electronics for N4 level. So we are going to focus on the question paper that I'm having, where we have questions that test to apply what we have on network theorems. So we just want to see how do we apply this concept whenever we are given such types of questions. So if you're new guys to my channel, you can consider subscribing so that you won't miss any of the classes that we shall be having for industrial electronics N4. So in this platform, we have the question one, which is the first question, that is to indicate whether the statement are true or false. You are given whether of this statement are true or false by writing only true or false next to the question number that is we are given in the answer book. Okay. So these are the questions that we are given, and also on 1.2 we are given to study the circuit below and apply the superposition theorem. So this one is still in our syllabus. That is why I have this question paper, because remember, some of the network theorems are being removed in the syllabus, so but this superposition is still there. So that is why I'm having also this question. So as you can see, a total of 18 marks there. All right, so the first question on 1.11 was to state the voltage loss test that the algebraic sum of all voltages around any closed loop in a circle is equal to 0. All right, so this is what we know about the voltage in a closed loop. All the voltages or the sum will be equal to 0, which is this one is actually true. All right, so according to what we have, this one is actually true there. All right, superposition theorem states that any network can be viewed as two terminal networks and can be replaced by a single source. This is actually false, guys. Why? This is for Thevenin, and we see know that Thevenin now they have removed the concept of Thevenin, but in this case this theorem is for Thevenin, so this one is false. That one is a false there. All right, then we've got 1.13. The first step when calculating a circuit with power source is to short one power source. All right, that is true in this case for maximum power. So this one is true. And what else do we have? In a circuit, if a circuit is one power source of Thevenin circuit, one should assume that the supply voltage equals VThev. No matter the condition that you be having, you have to calculate VThev. Okay, so this one you don't have any assumption that you do, so that's a false there. And on 1.15, the step when calculating maximum power transfer in a circuit is to calculate VThev and RThev. That is the first step. That is actually true. Remember guys, when you are having a circuit, you have to calculate VThev and RThev, the ones that you're going to use now to find the power. So this one is actually true. All right, so I think this part, guys, it was just clear and straightforward. Let's just see at the question that I want us to focus on, actually, which is on superposition. Actually, that's the question that I want us to work on. There we are given to study the circuit diagram below and apply the superposition theorem to calculate the current through the 9 ohm resistor, which is this one under R2. Take note, you work according to the circuit. They have given us the voltage V1 and V2, R1 and R3. Take note, this does not correspond. This is V1, R1, V2, R2. But this is what you have on your circuit in the question paper. You have to work with what you're given. You don't change this order that you're given. You work with the order that you're given. Okay, so as we know, guys, superposition theorem, this is just a revision of question papers, guys, that I'm doing here. The first thing that you're going to do is to remove one of the sources. Okay, so I'm just going to start with this one, V2. Depends, you can start with V1, it's your choice. You can start with V2, it's also your choice again. So that's the first step that I'm going to do. That's A, remove V2. All right, so the moment I remove this V2, as you can see, there's a resistor that is in parallel, so I'm going to be left with the resistor. So replace it, with 11 ohm resistor, which is R3. So replace with R3, which is the 11 ohm resistor. Okay, so this is the internal resistor. So that means the circuit is going to look like this. If I remove this part, I want you to see what is going to happen so that it will be easier for us. So this part I'm just going to replace with one like this. So one and the same thing. All right, this one like this, and this one is going to look like this. All right, so that is what is going to happen. Remember, we have removed this, so it's now like this. All right, so what is going to happen is that we have to calculate in this case. So this is according to A, so I'm just going to put it as R2A. I just that does not matter at all, guys. This part, okay. This is our R3 here, and we've got our V1, which is 30 volts. All right, so remember, we want to calculate the current that is going to flow here. So what we are going to do is to calculate the total current which is going to flow from this direction. All right, why are we calculating this total current? Because we actually know that this current is going to do like this. This is our I1A, this one. So it is going to flow this way and also flow this way. Remember your Kirchhoff's law, guys. All right, so you have the same application of Kirchhoff's when it comes to current. We are using superposition, but the flow of current remains the same. Remember, it will go into branch. So this will be your I2A, and this will be your I3A. So I'm just putting this A because that's my first condition, A. Okay, so that is the concept there. So in order for us to have this current, we can calculate this total current here, which is actually going to be from the, that is the total current, which is going to be from the total voltage over the total resistance of the circuit in this case. So where are we going to have this total resistance of the circuit? Because as you can see, V1 is there, but this one is not there. So we have to calculate RTA, which is the total resistance of the circuit. So as you can see, I want you to see something. Let's just close this part and see if we have this. Okay, so if we are to remove this part, this one, let me just put it this way. Are you seeing that these two resistors are actually in parallel, then connected to a series resistor? So that means it is going to be R1 plus, remember how you determine the total resistance in a parallel circuit is product over sum. So remember, product over sum. All right, so we are going to have R2 R3 over R2 plus R3 in this case, okay, which is so we put R1, which is 11 in this case, plus the product over sum, which is 9 by 11 like this, over 9 plus 11. So take note, R2 and R3, product over sum, you multiply them, then you add them, that is product over sum. So this is going to give us the total resistance, and we are going to have 11 plus 4,95 here. If you use your calculator properly, it's going to give us 4,95, which is actually going to give us 11,95 ohms. So which is I want you to also cross check in your marking guide there. If you are using this question paper, you see that they put an error there on the calc. I don't know, is the issue of the calculator or, but the stages were fine, but the value there was different. So take note, guys, this is going to give you 11,95 from your calculator. Okay, this is the RTA that we want to, in order so that we can have the total current, which is our I1. Why are we actually calculating this? Because we know that we can actually apply the current divider rule to calculate this current as long as this current is there. So let's calculate I1. This is going to be I1, which is a V1 over RT. All right, so V1 is there, which is 30 volts over the total resistance that we just calculated now, which is 11,95 like this. So we're going to obtain a decimal like 2,510 4, 6, and so on and so on. Okay, so you can just round off to 2 to 3 decimal places. As you can see, 4 cannot change this, so it's going to be 2,510 like that. So you just leave it like 2,51. All right, so this is I1 like this. So I'm going to put it on the diagram like this. We have calculated this and we obtained 2, so this is your 2,51 MC here. This is what it means. So this current is going to flow in here and also branch it this way. So as we know from our current divider rule that we can calculate this current from this current that we are given. How are we going to do that? Okay, let's apply our current, because remember we are focusing on this resistor, the 9 ohm resistor. We are not focusing on this one. That is why we have to calculate the current that flows in here. All right, so that will be current 2A, okay, which is this one that is flowing this way. So using current divider rule, remember you ignore this resistor and use the next resistor. So it's 11 over the sum of the 2 resistors. Okay, so you ignore this resistor, you use the next one. So it's 11, or let me just write the formula, R3 over R3 plus R2. So it's going to be R3 plus R2 times the supply current, which is the current that is flowing here, this one that is supplying the circuit. So you're going to multiply by I1. All right, so that is the formula that we are going to use there. So that's this resistor R3. So this is a current divider rule. All right, so R3, which is 11 over R3 plus R2, which is R3 plus R, you add these two. Okay, so it's 11 plus 9 like this. So you can just put this in a bracket, then you multiply to I1, which is this one that you just determined now. So those were actually the stages, guys, that you were supposed to work on. So you're going to obtain from our current divider rule, this is going to give us something like 1,3805, yeah, something like that. So you can round off to 1,81381 to 3 decimal places. So this is our I2A. So remember, guys, what we are doing here is that I want you to cross-check, guys, here. The current that is flowing in the 9 ohm resistor here is going to be determined from these 2 sources. So we have calculated the current, and due to the direction so that it's flowing this way, this current here. So this one is actually going this way, which is from the diagram here, this current is flowing this direction here. Okay, and that was on a condition when V2 was not there. So we are going to work now without V1, with V2. So which means you're going to take off V1 this time and see the condition of current that you're going to have. Then we combine the two. So that is the consideration there. So this is the first one that we just obtained. So let's move on to another step. This time we are going to remove V1. So this is B now. So we're going to remove V1. So as you can see, if we remove this V1, there is an internal resistor, this one. So you're going to replace with the internal resistor. Okay, so actually you're going to replace with the internal resistor, which is R1. All right, so you're going to replace with R1, which is 7 ohms. So take note, guys, about this. You have removed this voltage source, which means it is no longer part of our question. We are no longer having this. So the diagram is going to be like this time. All right, so this one is no longer there. If it was just like this, let's just say it was just a normal source like this, you are going to replace with a short circuit. So as you can see, is going to be a short. Suppose this one is not there, but because of the internal resistor, you are going to replace with the internal resistor. Okay, so this one is no longer there, and this part remains as it is. So this part is going to remain as it is, like this. So this is actually the stages that most of you don't even consider when answering, but it's very, very important that it guides you whatever that you are doing. This is 11 ohms, and this is R3, and this is R2, which is 9 ohms, and this is R1, which is 7 ohms. So this will be the circuit diagram now. So according to this circuit diagram, what we have to ask ourselves now is, how is the current going to flow? Okay, so from the positive, this is our positive, so it's going to flow this way, this direction now, and branch here and branch here. So as you can see, this is now our supply current, this one, which is from the resistor 3. So this is our I3, but due to the second condition B, so we're just going to write as 3B. This is I2B, this is I1B. All right, so as we can see, this current now is the supply, this one. So it is the one that we're going to use in order to find this current using our current divider rule. But how are we going to find this? Still following the last stages that we had, we have to calculate the total resistance of the circuit so that we can be able to calculate this current. So what will be the total resistance of the circuit this time due to this condition B? All right, because you have got a voltage source, okay, this is going to be in series but parallel to these two, because as you can see, these two guys are in parallel, these two, so they'll use product over sum. Okay, so it's going to be R3 plus these two guys in parallel, which is product over sum, that is R1 R2 over R1 plus R2. All right, so R3 this direction, or R3 this is 6, this is 11. Okay, so this is 11 plus the product of these two now. So we've got 7, and in R1 and R2, that is 7 versus 9 over 7 plus 9, like this. So product over sum. All right, so if we do this calculation here, we are going to obtain a total of 14,9375, yeah, something like that, which is going to give us 14,938. So this is going to change here into 8 amps. All right, this is ohms actually, this is resistance. Take note, guys, we are working with resistance here. All right, so this resistance is the total resistance of the circuit. So it's like we are now just having this voltage and the total resistance, so that will be able for us to calculate this total current of the circuit, because as I'm saying that I3B is the total current actually in this case, which is equivalent, now it's V2. We are not having V1, we are left with just V2. So it's V2 over the total resistance of the circuit. That will be the formula now. So that means you just substitute your V2, which is 12 volts, over RTP, which is this total resistance here, which is 14,938. All right, so that is the condition. So the moment I divide these two, I'm going to obtain this decimal 0.8033, something like that, okay, which is going to give us 0.803 amps. All right, so this is my total current, which is I3B, as you can see. So that means I'm now having 0.803 amps here, which is going to be divided here and here, because it is going to be separated. As we know, our current flows, so we have to find the current that is going to flow in this branch, because we are focusing on 9 ohm resistor, which is I2B this time. Okay, so let's use our current divider rule in this case, which is I2B, the current that we want to calculate. Remember, I told you you're going to use the opposite or the next resistor. You do not use this one first, you use the next resistor, this one that is parallel to, which is R1 on top. So it's going to be R1 over the sum of the resistors. All right, so it's R1 plus R2 times the current that is the supply current, which is the total current, this one, which is the supply current. All right, remember we said I3B is equal to IT. So whenever we are seeing I3B, we are seeing the total current, that is your total current there. All right, so that will be R1 in this case, which is 7. So as you can see here, we are having 7 over the total in this case. So we are going to have 7 over the total, which is 7 plus 9, 7 plus 9 like this, times I3B, which is the total, which is 0.803 like this. All right, so that is what we are going to have in this case. So that means we are going to obtain a decimal like 0.35. Yeah, that's 3513125, something like that. Okay, which is going to give us 0.35123 decimal places. Okay, so that is our I2B like that. All right, then now let's finalize here, guys, what is happening. According to the two separate circuits that we had, okay, this was the first circuit that we have. In the 9 ohm resistor, we determined I2A. Take note about the direction, is flowing this way, okay, which is our I2A. On the second condition, we separated, our I2B was also flowing the same direction. On the other separate diagram, our I2B was flowing in the same direction. So you're going to add these two currents to determine the current that is going to flow in the 9 ohm resistor. So that will be the sum of the two. So therefore, I2, which is the current in the 9 ohm, that is current in the 9 ohm resistor. All right, this is the one that we are referring as I2, will be equal to the total of the two, I2A and I2B, because they are flowing in the same direction. All right, so let's substitute now. Our I2A is here, first one that we calculated, remember, this one that we obtained 1.381 plus our I2B, which is the one that we just calculated now, which is this one. That's our I2B, this one is 0.351. All right, so we now add the two, which is going to give us 1,732 amps. So that is now I2, which is the current in the 9 ohm resistor, the one that you are being asked to calculate. So as you can see, that's how these questions mostly on superposition, these are the steps that you're supposed to apply or to take. So as you can see, guys, we're having a total of 18 marks on this question, which was one of the question papers. So as you can see, that's how they ask these questions. And not to miss these classes, consider subscribing to my channel, Maths African Motives, and come back for more question papers, questions from question papers, as we shall be working on industrial electronics and form till we meet again.